All right, so in the previous video, we introduced the multi-head, but then we said there's a way to make it a bit more efficient than the way we were doing it. So now that's what we are trying to see now. How do we make it more efficient than we had? We saw that we are using a for loop to create that forward pass, but in this video, we just want to make it more efficient. And this video will be the last theoretical parts of this course of this chapter. And then in the next video we'll just summarize and we'll go on to the next chapter. But let's not rush. How are we going to make it more efficient? We're going to do let me not say multiple here. So multi-head attention with weight splits. Weight splits. All right. So what we know, what we've done so far is we've stacked the head attention modules, right, in that for loop and all of that. And then at the end, we merged them. Into the context vectors. But so far, we've been maintaining the multi-head wrapper, you could even called it a wrapper, and the causal attention. Right now, we just want to put them into one class. We want to put them into one class. And also, on top of putting them into one class, we then add these weight splits. We'll see what that what that weight splitting means just now. So what we are going to do is what we had initially. So before I go to the code, let me first show you what we're trying to do. Because when you look at the code, you might be scared when you look at the code because it is quite complex. It is a bit complex. But especially if you've never done PyTorch before, it looks quite scary. But don't be scared. The codes are already there. Read line by line as many times as you want to actually get what is going on. But for now, we are explaining the principle of what is going on, which should make sense intuitively, and then we will see the code. So we have our inputs here. So what we had before when we had that multi-head wrapper, multi-head attention wrapper with our causal attention, what we had was we had our inputs, and the inputs were being split. For example, when we're calculating queries, we would then have our weight matrix here. We would have our weight matrix, which was our WQ1. And when we applied that WQ1 to our inputs, we then came up with our queries matrix, right? Q1. And the application here was a what? Was a multiplication. We had a matrix multiplication there. That's the same thing. Depending on how many heads we had, we'll do the same thing because here we would have another weight matrix. We'd have another weight matrix, which is WQ2, which would give us queries to Q2. That was our for loop, right? That's what it was doing. For we had in the number of heads that we have, we'd do this, and then we'd have a queries one. We'll do that again, we have a queries two, and we'll do the same for values and keys. So we'd have a keys matrix here, K1 and all of that, and we'll do the same thing. Here we are performing two matrix multiplication operations. We're performing two uh, multiplication operations, as you can see. And those are just for number of heads equal to 2. And these are just for queries. We also have to do the same for keys. We have to do the same for vector for values. So which means if we have 2 heads, we are doing 6 matrix multiplications to do this. That's what we were doing before. But then now what we are now looking at is the weight splits and seeing how that makes it efficient. So now this is what we are doing. We have our inputs X. What we are going to do is we are going to initialize a big weight matrix. So this weight matrix We're going to initialize this WQ, a very large WQ, very large WQ, which we have its dimension out, the D out equal to 4. Here our D out, the D out that we're using was equal to 2, with our D out equal to 2. But then now we are initializing a big weight matrix, which is a dimension out equal to 4. How do we get this 4? We get this 4 by this dimension out, the original dimension out, right? Multiplied by the number of heads. We are going to see this formula here, multiplied by the number of heads. So how many heads are we dealing with? 2. And what was our D out for the individual weight matrices? It was 2. So 2 times 2 equal to 4. So we have this big matrix that is 4 as the D out. And we then apply that, we do our matrix multiplication. When we do our matrix multiplication, we're going to get a big queries matrix. We're going to get that big queries matrix. And then it will also have D out equal to 4. That's the dimension. And after doing that, we are then just going to split this big matrix into smaller matrices. Queries Q1, and we'll have query Q2. Queries Q1, and we have query Q2. Here, that's where the split happens. Split happens. We turn these big queries into query 1 and query 2. And then here, this is matrix multiplication. As you can see already, in the now that we are proposing here, we are doing only one matrix multiplication. We are not doing multiple matrix multiplications like we were doing when we were splitting, when it was split. Here you say, but 1 and 2 is not really that different. But imagine if our number of heads, like I mentioned, that some of these models, the large language models, they have multiple heads. 24 is very little. Some of them will have 96 heads. If you have 96 heads, in this scenario, you would have done matrix multiplication 96 times on large matrices, because these matrices will not have D out equal to 2, might have a D out equal to 12,000 and all of that. So these are big matrices. And to do that, these matrix multiplications 96 times just to get 96 queries. And then after the 96, you have the key. You need to do the same thing for keys. You have to do the same thing for values. It becomes very inefficient. So in our now phase, we will just say, oh, number of heads that we want is 96. Okay, what are the dimensions? And we create the big matrix, and we have one operation, one matrix operation, multiplication, and then we have our queries. And then we do another matrix one matrix application multiplication, and we have our keys, values, queries, all of that. Just 3 times, 3 applications. And the split here, the split is very, very simple. The split is done by transposing. It's done by transposing. We're going to see how we apply the transpose. But this is now what is going to be in our multi-head, combined multi-head attention class. So we are not using the wrapper anymore, because inside multi-head attention, there are principles that are coming from the wrapper, there are principles that are coming in from the causal inference class that we had, and there are also principles that are coming in here for efficiency. So now that we have that integrated approach, which is different to the previous class with stacked multiple head attentions, let's see what it's going to how it's going to be like in code. Again, in code, it is looking very nasty and complicated, but if you understand the principle that we have just discussed now, that's all there is there. So now let's see. We want to do with our weight splits. So do not worry, I'm not going to also get into the codes themselves, um, because it will take time for us to explain each and every line. But you remember there when we were doing for the big matrix, we were saying D out is going to be equal to the dimension of the head multiplied by the number of heads. Here we are just calculating the head dimension because it's easier because we know what our dimension of the output that we want. We can set that. The number of heads we want, we can set that. And using those two, we can just rearrange the equation and calculate the head dimension. Nice. And then here we have our big query, the big matrix query, which is our D in and our D out. And we have our D out. And here we are setting that the D out must be divisible by the number of heads. Yeah. And then we have our we have our key again. This is going to be the big key query, big key matrix, and then the big value matrix, which has everything. And oh, that's all we are doing then. And we have our dropout, we have our mask, and all of that. In our forward, we calculate our KQV here. And by doing our KQV, we use something called view. We use this dot view in PyTorch. So when we're splitting these, because these are the big keys, the big Qs and the big values. So those we need to then get into splitting, right? The splitting of the query key and value tensors, it is achieved through tensor reshaping and transposing the operations when we are using this dot view and transpose methods. So we're doing the reshaping here. The input is first transformed via these linear layers that we're doing for queries, keys, and the values like we did here. We apply the key query value to our input and means we're transforming it with those linear layers and we get our keys, queries, values, matrices. Then our important operation here is to split out the D dimensions. This D out dimension, that big matrix, is to split it into multiple number of heads. Because if we now say 96, our D out needs to be split, that big matrix needs to be split into 96. 96. As we can see, let me show you what stage we are at. We are at this stage. We have calculated this. This is the query matrix that we calculated using that linear layer. Oh no, we calculated, no, this is the weight matrix. We actually calculated this query. We calculated this query and we also calculated its counterpart, the keys, in the same manner. And we calculated its values, right? We use matrix multiplication with the respective weight matrices. So we have this big matrix. We need to split it out. Here we are using two heads. So it's the queries are going to be split into two smaller queries, Q1 and Q2. The keys are also going to be split into two, K1 and K2. The values are going to be split into two as well, V1 and V2. If we had 96, we're going to split them into 96. So the split happens here based on the number of heads. Number of heads. That's what I was trying to say. The split happens, the D out is split based on the number of heads. So if the number of heads are 2, our output here will now be D out equal to 2. That's why we have to assert that our D out that we put in there for the big matrix is divisible by number of heads because we want them to be divisible like this. So that's why we have to assert it in code. So let's go back to code and see. So now that we've done that, we now reshape and we reshape the we are reshaping now. So we are splitting the D out dimension into multiple number of heads and the head dimension. Where that head dimension was that formula that I said, head dimension is equal to D out divided by the number of tokens that we asserted here. So that is our head dimension. That is the head dimension. And that here dimension is the one that is the smaller matrix, the dimension of the smaller matrix. The smaller matrix, we have that D out divided by the number of dimensions, now the number of heads. And we are doing that using this view. So we're unrolling the last dimension because the last dimension, the dimensions of these, the shape is B, which is the batch, number of tokens, and the D out because it's a big matrix. So we want to split out this big matrix and we use the view, which then splits to then be the shape, it will be B, our batch, number of tokens. And then we have our number of heads and the dimension of that smaller matrix that we want. So the smaller matrix will be, okay, how many matrices are we going to have as the smaller ones? In our example, we had two, and each one is going to have some dimension, maybe three, maybe two, whatever it's going to be. In normal LLMs, it will be like whatever, thousands and thousands. So that's all we are doing with the view. And we do the same for values. We use the view to split out this last dimension into these. So now we have created smaller matrices in here. And once they are created, we then transpose them. The reason why we are now transposing, right, is because we want the tensors are then transposed because we want to bring the number of heads dimension before the number of tokens dimension. So transposing, we are pretty much just uh, in simple terms, we are rotating the matrix. We are rotating the matrix so that the axes they just move. So instead of having the x matrix as it was, maybe the x axis would then become the y axis, and the y axis becomes the x axis. We're just rotating, sort of rotating the matrix. So when you transpose them, now we are having a different. We are going to have this as our shape. So now the B will remain the number of batches, and we are moving the number of heads to be here before the number of tokens. We are just rotating them. And then we have the number of tokens, and we maintain the dimension. So we just rotated it. That's what we're doing here. Perfect. The keys are rotated, the queries and the values as well. And after we have done that, we do that so that at least we align the query keys and values across the different heads that we will be using and performing batched matrix multiplication more efficiently. It looks complicated, but the principles are the same as we did previously with a bit of efficiency added to it. And then now we compute our scores. Our attention scores are computed the same way. Our queries are multiplied by the keys, the same way we did previously. And then we then do the masking, and then we do the attention weights with our softmax. And after doing the attention weights with our softmax, we then calculate the transport vector, the context vectors. We do our context vectors, and then here we just clean it up so that at least they have the right type of output that we want, the right type of shape, and the right type of output. And then we just return the context vectors. So that's pretty much what we're trying to do here. It's essentially the same that we've been doing, just combined and with a bit of efficiency. And we just apply it. We apply it there with a bed size, with our bed size and our D out, and we get these as the result. That's it. That's it. This is now a more efficiently written version of our multi-attention wrapper that had causal inside it. So causal is now inside here as well. You see the masking happen. Causal is in there, but just in one class. It might look a bit different, but it's just because of weight initializations. You can just see here. And we added a linear projection, which is just out projection. It is just a transformation that we added there. But the core of it is the same. So congratulations for getting to this stage of the course. Like I said in the beginning, you have understood a very complicated part. So let's summarize what we have just done in the next video so we close out the chapter.